Okay, so if you recall from a couple classes ago, we were trying to find this best linear unbiased estimator, or we were trying to prove that least squares is the best linear unbiased estimator. So this is from the application exercise 5, and so I just thought we would walk through the derivation here. What this is doing is trying to come up, if you recall, CY was our alternative linear unbiased estimator that we're trying to compare least squares to show that least squares is best. And so the first thing we need to do is to develop this estimator here, this CY, and make sure that it's unbiased. So we want that the expectation of CY given X, in order for this to be unbiased, what needs to be true? So in order for this to be unbiased, this needs to be equal, this here needs to be equal to beta. All right, so we want this to be equal to beta. I've written out the beginning of the equation here for you by just plugging in what we designated as CY. So CY is X transpose X inverse, X transpose plus D, so that's the C part. And then Y, we can plug in X beta plus epsilon, because we know that's our equation for Y. And then we still have given X. All right, so let's take the expectation of this. Before I actually take the expectation, though, I'm going to underline the parts of this equation that are fixed. Why am I doing that? Because if I underline what's fixed, I know what I can pull out of the expectation and not have to worry about. And there's a lot here that's fixed. So remember that this is given X. And so all of this here is fixed. X beta is fixed. The only thing that's random is epsilon. So that's going to be the only part that I'm actually worried about in terms of the expectation. So the first thing I'm going to do is just distribute this X transpose X inverse X transpose plus D to this X beta plus epsilon. And I can pull out the components that are in the blue underline of that equation. I can pull those out of the expectation because they're fixed. So I end up with X transpose X inverse X transpose plus D. There we go. So I end up with X transpose X inverse X transpose plus D times X beta plus X transpose X inverse, put parentheses here, X transpose X inverse times X transpose plus D. So I'm just distributing this to the X beta and the epsilon. And so I was able to pull all of these pieces out of the expectation because they are all fixed. But that one random part, that epsilon, has to stay inside. And so I'm going to pull that expectation, epsilon given X. So I've got X transpose X inverse X transpose plus D times X beta plus X transpose inverse X transpose plus D times the expectation of epsilon given X. Okay. All right. So what do we know about this? We know that this is equal to 0. So this is going to be 0, which is going to cancel out this whole part of the equation. And so that leaves us with just this, X transpose X inverse X transpose plus D times X beta. So now I'm going to distribute the X beta. And so I end up with X transpose X inverse X transpose X beta plus dx beta. So I just distributed the X beta to each of these components. Okay, now what can we do with this right here? Well, it turns out this X transpose X inverse X transpose, what is that? If you multiply an inverse of a matrix times itself, what happens? You just get the identity matrix, so we can cross that out there. And so now we've got beta plus D times X beta. So this is going to be equal to the identity matrix plus dx times beta. And so how do we get this to equal just beta? Well, basically we need this dx beta here. We need the dx to go away. We want just the identity matrix times beta. And so in order for this, the expectation of cy given x, of our linear, of this linear estimator, in order for that to be equal to beta, we need this dx to go away. And how would that dx go away? Well, we would need dx must equal 0. So this is going to be an important fact that we're going to use in the next step here. So what we've shown here is that the expectation of our this linear estimator that we've come up with, it is unbiased for beta as long as dx equals 0. And so in order for this to be an unbiased estimator, we need that dx to be 0.